Today I will present our research work on how we can distinguish legitimate traffic from spoofed. Here is an example of a topology consisting of three ASs. And let's take the perspective of AS1. AS1 expects traffic coming from AS2 to traverse their direct link, as this generates profit. However, we may see traffic from AS2 arriving at AS1 through AS3, and this can be either a misconfiguration or maybe AS1 failed to advertise the route to AS2. In that case, the network operator in AS1 can use packet counters, generally speaking as flow data, to detect this and start troubleshooting this network issue. However, what in reality can happen is that we may see traffic with the IP addresses of AS2 coming through AS3, and this traffic can be spoofed. In that case, the network operator in AS1 will start troubleshooting a network issue that doesn't exist. So how we can effectively distinguish legitimate traffic from spoofed traffic to minimize false alerts? Unfortunately, control plane techniques cannot solve this problem, and the only solution that we have is to look on the data plane. In this work, we look for legitimate traffic, and by legitimate traffic, we refer to traffic that originates from the location it claims to be from. The big idea here is that if we are able to detect legitimate traffic, we can use it as a routing signal, and we can build a system on top of this that minimizes false alerts and raises alerts only when legitimate traffic arrives at unexpected locations. As many of you will be wondering, how easy is to detect legitimate traffic? The short answer is it's not easy at all, as many factors impact the traffic that we see. These factors include external network conditions, for example packet loss, the implementation of transport protocols, and potential malicious users. However, there is a fundamental difference between legitimate and spoofed traffic. Legitimate traffic typically consists of some closed-loop flows where the sender sends some data to the receiver and elicits a response from the receiver in order to send more data. In this work, the big idea is that if we are able to detect closed-loop flows, we can use them as a proxy to detect legitimate traffic. So how we can detect closed-loop flows? We can do this by tweaking traffic and observing the resulting interactions. To identify a closed-loop communication, we need a module, we'll call it checker, that monitors the exchange traffic. In this example, we place the checker in the path between the sender and the receiver. Unfortunately, as the routing on the internet is highly asymmetric, we expect the checker to see only one direction of the communication. To determine if the flow is closed loop, the checker can tweak the traffic and wait for the action to reflect back. Our action will first reach the receiver, then be passed to the sender, and finally return to the checker. We consider TCP as the best candidate since it's inherently a closed loop protocol. So, what is the easiest and simplest action that we can do in order to trigger a well-defined TCP action? We can drop a packet, as TCP ensures the reliable retransmission of the data. So far, the idea sounds simple and straightforward. We drop a packet, and if we observe a transmission, the flow is closed loop. If we don't, the flow is not closed loop. But is it that simple? Unfortunately not, as after we drop a packet, many things may go wrong. First, the retransmission packet may reach the receiver through a path that bypasses our monitor. In that case, we will wrongly characterize the closed loop flow as not closed loop. Secondly, we may drop a packet from a spoof flow where the sender deliberately sends duplicate packets in order to mimic retransmissions. In this case, we will wrongly characterize the spoof traffic as closed loop. It becomes obvious that by just dropping a single packet, the signal is weak and noisy. Can we do better? Yes. And the better approach is, instead of dropping a single packet, to drop a few packets until you get enough confidence in the nature of the traffic. And now let me introduce you to our system Penny. Penny is a traffic checker designed with a statistical model as its core, consisting of two competing hypotheses. The first hypothesis is that the flow is closed loop, and the second hypothesis that the flow is not closed loop. Penny drops packets with an equal probability and gains confidence in one of the two hypotheses based on the outcome of a packet drop. After a few packet drops, we expect one of the two hypotheses to dominate the other. Here are the maths. Our model consists of counters, parameters, and probabilities. The maths evaluate the likelihood that a closed-loop flow generates the observed retransmission, take into account potential missed retransmissions and receiving duplicate packets. And now to help you, I will give you intuition of how the maths work. Here is how the two hypotheses look when the flow is not closed loop and when it's closed loop. We can see that as the number of packets increases, one of the two hypotheses tends to zero. So far, we have assumed that there are always enough packets for Penny to successfully reach a conclusion after a few packet drops. But what happens when all TCP flows are short and we cannot drop enough packets to reach a safe conclusion? We address this by aggregating multiple flows. This approach allows us to apply the same statistical properties with significantly less impact to the individual flow, as we do not drop many packets from each flow. Penny sounds like a straightforward mechanism where we drop a few packets, and if most of them are retransmitted, we consider the flow as closed loop. However, transitioning Penny from theory to practice exposes lots of challenges. The first type of challenges has to do with the TCP protocol itself. For instance, after we drop a packet, for how long we should wait for a retransmission packet? And do we expect to see exactly the same packet retransmitted? Or can the drop data be concatenated with fresh data? Moreover, what we should do in cases where we drop a packet and after that we observe a reset packet? Apart from these TCP complications, we have also network challenges. What if we have additional packet loss? Or even worse, what if the routing changes and we stop seeing new packets? Finally, there is the challenge of malicious users trying to bypass Penny by mimicking retransmissions. How we can protect Penny from such scenarios? To make Penny robust and reliable, we had to handle all these complications and many more. To deal with all these complications, we create a set of mechanisms. And for this mechanism, the fine detail matters, so I will explain a few of them in the next slides. The first mechanism that I will focus on is when we drop a packet, for how long we should wait for a transmission. When we drop a packet, we set a conservative expiration timer of 3 seconds. We also store all current measurements up to that point. When the packet timer expires or the packet gets retransmitted, we evaluate the hypothesis with the stored measurements. But what if we receive a thin packet while we wait? Are we expecting the packet to be retransmitted? Yes, it should, as a correct TCP implementation should retransmit any packets that precede thin. On the contrary, when we drop a packet and we observe a reset packet, what we should do? In this case, we should consider that reset packets indicates that the TCP connection was interrupted, and thus the drop packet may never get retransmitted. Therefore, we discard anything related to this packet drop. Now let's see another complication. What if a source always sends a packet and a duplicate immediately? If we drop the first copy of a packet, we will only consider the second as a retransmission. Can we just ignore duplicates? The answer is no, as duplicates may be the outcome of downstream loss. We know that TCP does not cope with too many duplicates. Therefore, if we track the number of duplicates and it exceeds our threshold of 50%, we can flag it as suspicious. If a source sends less than 50% of duplicates and we drop a few packets, we are not gonna get them all right. So, does it work? In order to answer this question, we did multiple experiments using the NS3 simulator. We tested multiple TCP variants, different network conditions, a different set of input traffic, and we also examined a variety of Penny parameters. Let's now look at some results when only closed-loop traffic is present. This plot summarizes results on many simulations in different settings. In this figure, the x-axis depicts the number of packets observed by Penny, and the y-axis the number of drop packets. Each point represents the outcome of Penny's statistical model. Orange points shows cases where the outcome is closed loop. As we can see, all points in the plot are orange, meaning that Penny always correctly classifies traffic as closed loop. We then evaluate scenarios where all traffic is spoofed. The worst case scenario is an attacker to duplicate packets just below our 15% threshold. Therefore, we run experiments with traffic patterns that randomly duplicate up to 14.9% of packets. The plot is similar to the previous one, except that there are blue points representing cases where Penny model reached a decision that traffic is spoofed, and grey points meaning that the threshold of maximum duplicates was exceeded. As we can see, in the vast majority of cases, our statistical model concludes that traffic is spoofed, or duplicates exceeded. However, with low number of packet drops, there might be cases where the model concludes that the traffic is closed loop. It becomes obvious that relying on a few packet drops is risky as we rely on stats. We therefore have a threshold for the minimum number of packet drops before reaching a conclusion. By default, we use a conservative threshold, namely 12 packets. Our theoretical analysis indeed guarantees that when using 12 packet drops as a threshold, the chances of wrongly characterizing spoof traffic as closed loop are 1 in a million. With this threshold, we see that the outcome is always correct. So far, we have seen how Penny behaves when traffic is either closed loop or spoofed. What if some closed loop traffic is mixed with spoof ones? We run experiments with different fractions of closed loop on spoof traffic. In this figure, we depict the case where the ratio between the two is 50-50. As we can see, in many cases we reach a closed loop decision, which aligns with our system goal to find closed loop traffic when present. However, there are also many cases where the stats conclude that traffic is spoofed. To handle these cases, if Penny outcome is spoofed, we start testing individual flows. In our evaluation, we found that when switching to this mode, we are always able to find some legitimate flows. We also evaluated the performance impact when running Penny on individual flows and when running Penny on aggregates. We found that Penny has a minimal performance impact on the completion time of TCP flows, especially in the case of aggregates, as we carefully drop 12 packets across multiple flows. We also examined the feasibility of running Penny, and we found that as we mostly update counters, Penny has low processing and memory requirements. And now let me summarize the main takeaways from this work. First, we introduce Penny, a robust, reliable, and practical traffic checker that interacts with transiting packets to assess if they are part of a legitimate flow and thus they are not spoofed. We have shown that by carefully dropping a few packets, you can get a strong signal and you can have minimal impact on the performance of legitimate TCP flows. We hope that network operators will find Penny as a very useful tool to get better understanding on traffic ingressing to their networks. Thank you.